Let us now do some exercise problems from exercise 1.1 of chapter 1. This exercise deals with the concept of the fundamental theorem of arithmetic, which is the representation of composite numbers in terms of their prime factors. Okay, so the first question is asking us to express each of these numbers in terms of their prime factors, as a product of their prime factors. Of course, I'm not going to do all these 5 examples. I'll just do 2 or 3 of them. Okay, so to begin with, I will do it for 140, which is quite simple. And the way we will proceed for that is we'll start dividing the number 140 with some prime number. So since it's 140, just to speed up things, a prime number that goes into 140 is the number 7. Okay, so 7 goes into 14 2 times, and then we have a 0, so we bring it down. So it's 7 goes 20 times, and then we have 20, so it's 2 going into 20 10 times, so 10 again, so 2 goes into 10 5 times, and 5 is a prime number, so only 5 goes in 5 1 times. Okay, so the prime factor representation of 140 is going to be the product of these divisors, so which we divided with, and all these are prime numbers. So it is 140 is 7 into 2 into 2 into 5. Okay, so that's the prime factor representation of 140. Of course, when we want to represent this using the prime numbers in ascending order, then we can write it as 2 into 2 into 5 into 7, and when some number appears multiple times, we can use the power representation. So it's 2 power 2 into 5 into 7. Okay, so that's the prime factor representation of 140. Similarly, we can do it for 156 and 3825 and so on. I'll do it for 5005. So 5005. So again, since it's ending in the digit 5, let me keep some space on the left so it's easier to write. 5005. So that's 5 ones are 5, 001. So it's 1001, and we'll need to check whether any other prime number goes into 1001. So we can continue dividing this 1001 by checking if any other prime number goes. So when we checked with 3, it does not go. The next prime number is 5. 5 does not go in that also because it does not end in 5 or 0. So we check with 7 now. 7 goes, in fact, 143 times. And then we see whether which is the next number that divides 143. The number 11. Okay, the next prime number that goes into 143 is 11. 11 goes into 143 13 times, and 13 in fact is a prime number, so 13 goes into 13 1 times. Okay, so now we can represent 5005 as a product of its prime factors as 5 into 7 into 11 into 13. So if you multiply this, you will say that you get 5005. Okay, so when solving these problems, it is important that you are thorough with your tables. So I suggest that you memorize tables at least up to the 20th table. That way, it will help you in all these calculations. Okay, if you are not thorough with your tables, these calculations might seem more difficult than they actually are. Okay, so it is important to revise your tables, and it will be helpful in solving these problems. These are pretty straightforward and simple problems, but if you don't know your tables, it may take you much longer to solve these problems than required. Okay, so let's move on to one more example. I'm going to do the next one, which is 7429. So 7429. Let's divide this with some prime numbers and see which prime number goes into this. Now if you start checking the division of this with each of the prime numbers, So of course, since it's an odd number, we can't divide it by 2. The next prime number that we can use for the division is 3, and you will find that 3 also does not go into this, 5 does not go into this, 7 does not go into this, and the next prime number that will actually go into this, okay, not 7, not 11, not 13, and the next prime number that goes into this is 17. So 17 goes into this. So when you divide 7429 by 17, you get 437. So the only prime number, the first prime number that goes into 7429 is 17, and 17 goes in 7429 437 times. And again, if you check that's when the 17 goes in 437, we find that 17 does not go in 437. So the next number, the next prime that we can consider dividing is the number 19. So the next prime is 19. So dividing 437 by 19 gives us 23. So 19 is the next prime that can be used to divide here, and that goes 23 times, and 23 again is a prime number. So the only number other than 1 that goes into 23 is 23. So the prime factor representation of 7429 is going to be 17 into 19 into 23. Okay, so we can't split 17 or 19 or 23 into smaller parts in terms of their prime factors, because they themselves are prime numbers. 17 is a prime number, 19 is a prime number, and so is 23. So the prime factor representation of 7429 is 17 into 19 into 23. Okay, so this is important because the prime factor representation is used subsequently for finding the HCF and LCM. So you need to be pretty clear with the prime factorization in order to solve the next set of problems. Okay, this is fairly straightforward and easy, and it's something that you have done several times in your earlier classes, in class 9 particularly. But in order to do this quickly and accurately, you need to be thorough with your tables. Okay, so let's move on to question number 2, which deals with finding the LCM and HCF of pairs of numbers, and it is asking us to find the LCM and HCF and also verify the relationship that when we have pairs of numbers, the product of the HCF and LCM is equal to the product of the two numbers itself. So let's start with the first one. You'll find the HCF and LCM for 26 and 91 by using the prime factor representation. So let's first write down 26 and 91 in terms of their prime factors. So 26, of course, we can write it as because it's an even number, we can divide it by 2. So 2 will go into 26 13 times. So it's 2 into 13 is 26. And then 13 is a prime number, so we cannot divide 13 any further. So the prime factor representation of 26 is 2 into 13. 2 13s are 26. Similarly for 91, so the prime factor representation of 91 is going to be 7 into 13. Okay, so the smallest prime number that goes into 91 is 7, and it goes 13 times, and 13 being prime, the only further division is 13, goes into 13 one time. So 91 is 7 times 13. Okay, again you can divide it and using prime numbers as we have done in the previous case. Okay, you can go ahead in this procedure to find the prime factors and then represent them as a product of the prime factors. So now that we have the prime factor representation, the HCF is the common terms, common prime factors in both the prime factor representations. So the common term here is the number 13. So the HCF is HCF equals 13. So that's the only common term. So if you recall the definition from the earlier class, that the HCF is the product of the smallest power of the common prime factors. So the common prime factors that are available in both these factorizations is the number 13, and the smallest power of 13 that is present there is 13 power 1. So the HCF is 13. Now, to find the LCM, we will again write the prime factor representations of these numbers. So 26 is 2 into 13, and 91 is 7 into 13. So the LCM in this case is, if you recall the definition, it is the product of the greatest powers of each of the prime factors, but the greatest powers need not be common. So the prime factors involved in the factorizations of 26 and 91 are 2, 7, and 13. So the greatest power of 2 is 2 power 1, the greatest power of 7 is 7 power 1, and the greatest power of 13 is 13 power 1. Okay, so the LCM is going to be 2 power 1 into 7 power 1 into 13 power 1, which is basically 2 into 7 into 13, and that gives us 196, I believe. Okay, so it's actually 182. Okay, my apologies, it's 182. So the LCM is 182, and we can verify that the HCF multiplied with the LCM is equal to the product of the numbers. So HCF into LCM equals HCF is 13 and LCM is 182, and that is equal to 2366. Okay, so HCF into LCM is 2366. That's 2366, and the product of the two numbers, which is 26 multiplied with 91, that should also be 2366. Let's verify. So 91 into 26 is in fact 2366. So when you multiply, you will find that you get 2366. So this is one relationship that we have seen when we have the HCF and LCM for two numbers. So the product of the HCF and LCM of a pair of numbers is equal to the product of those numbers itself. Okay, so now we have seen how to calculate the HCF and LCM. So let's do one more example here. So I'm going to do for 510 and 92. So let's represent 510 in terms of its prime factors. So the prime factors of 510 would be, so let's calculate the prime factors. I'll do the calculations at the side here. So 510. So since it's an even number, so we can divide it by 2. So 2 goes into 5 2 times. Then we have 11. 2 5s are 10. The remainder is 1. 2 5s are 10. And it's ending in 5, so we can divide it by 5. So it's 5 5s are 25. 5 1s are 5. And then we have 51. So we can divide 51 by the prime number 3. 3 1s are 3, remainder is 2, 21, 3 7s are 21. 17 is prime, so that means we can divide it only by 17, which goes 1 times. So 510 can be represented as the product of prime factors as 2 into 5 into 3 into 17. Okay, that's the prime factor representation of 510. And now we can write the prime factor representation of 92 as well. So for 92, again, since it's an even number, we divide by 2. That's the first prime number, which is 2. So that's 2 4s are 8 and 2 6 are 12. So again divide by 2. 2 2s are 4, 2 3s are 6, and 23 is a prime number, so 23 will go only one times. So 92 can be written as 2 into 2 into 23. So the HCF is the common term that is present in both the factorizations. So there is only one common term here, which is this 2. There is no other common term that is present in both the factorizations, right? So the HCF is simply 2. HCF equals 2. Similarly, we can go ahead with computing the LCM by writing again the prime factors. So 510 is 2 into 5 into 3 into 17, and 92 is 2 into 2 into 20, that's into 23, and we can write this as 2 power 2 into 23. So for finding the LCM, we take the product of the greatest powers of the prime factors. So the greatest power of the prime factors that are involved. So there is 2 involved. The greatest power of 2 that is involved in the prime factorization is 2 power 2. So we take that 2 power 2. And we have a prime factor of 3 in both these in these two factorizations. Of course, for LCM, we need not check whether it is common. So the next prime factor that is present in both of them is the number 3. Okay, when you combine both of them. Okay, I don't mean to be that it has to be common. So the prime factor of 510 and 92. If you look at all the different prime factors that are present, 3 is one of them, and the highest power of 3 that is present in this is 3 power 1. So we'll put as 3 power 1. The next prime factor that is present is 5, and the highest power of 5 that is present is 5 power 1. And then we have 17, so into 17 power 1, and then we have 23, so that's 23 power 1. So the LCM is 2 power 2 is nothing but 4, into 3 power 1 is 3, into 5 power 1 is 5, into 17 into 23. So the LCM in this case is the product of these numbers, which is equal to 2 into 2 into 3 into 5 into 17 into 23, which is 23,460. So that gives us 23,460. Now again, we can verify that the product of HCF and LCM is indeed equal to the product of the two numbers. So HCF into LCM equals 2 into 23,460, and that is equal to 46,920, and the product of the two numbers, 510 and 92, that should also be 46,920. So it's 510 multiplied with 92, that is indeed 46,920. So it is verified, 46,920. Okay, so in a similar way, you can find the LCM and HCF of any pairs of numbers. So I'll leave the next one as an exercise for yourself to practice. Okay, so we'll move on to the next question, which involves finding the HCF and LCM of three numbers by using the prime factorization method. So I'll do let's say a couple of problems. So I'll start with the first one. So again, for 12, the prime factor representation is 2 into 2 into 3. So that's 2 into 2, 4 into 3, 12. For 15, it is simply going to be 3 into 5. And for 21, we'll have 3 into 7 is 21, right? So these are the prime factor product representations of these three numbers. So HCF is going to be the common term that is present in all the three is 3, so the HCF is 3, and the LCM is the product of the greatest power of the prime factors that are present in each of them. So the prime factors involved in these three representations are 2, 3, 5, and 7. So we have to take the greatest power of 2, the greatest power of 3, the greatest power of 5, and the greatest power of 7. So the greatest power of 2 that is present here is 2 power 2, because we have two 2's here, right? So this is 2 power 2 into 3 power 1. So this is 3 power 1 into 5 power 1. This is 3 power 1 into 7 power 1, right? So the LCM is the product of the greatest powers of each of the prime factors that are involved in this factorization. So the greatest power of 2 is 2, so 2 power 2 into the greatest power of 3 is 3 power 1, so we take 3 power 1, okay, we take it only once, okay, and then the greatest power of 5 is 1, so it's 5 power 1, and the greatest power of 7 is also 1, so it's 7 power 1. So basically we have 2 power 2 is 4 into 3 into 5, that is 60, and into 7, so that should be 720. Okay, so the HCF of these three numbers is 3, and the LCM of these three numbers 12, 15, and 21 is 720. Just a small correction in the multiplication here, it's not 720, it is 420. Okay, make that correction. So it's 4 3s are 12, 12 5s are 60, and 60 into 7 is 420. Okay, my correction. Okay, please note that. So it is LCM is 420, and the HCF is 3. Okay, let us now look at the second question, which is slightly interesting. So we have 17, we have 23, and we have 29. So what is the HCF of these three numbers, and what is the LCM of these three numbers? If you notice, all these three numbers are prime numbers themselves. They are not composite numbers, right? So the prime factorization, the only prime factorization available for these numbers is the number itself and the number 1, because they are prime numbers. So the only numbers that divide the prime number are the number 1 and the number itself. So 17 can be represented in terms of its prime factors as 17 into 1. Similarly, 23 as 23 into 1, and 29 as 29 into 1. So therefore, the HCF of these three numbers is 1. So the common term available is the number 1. So 1 is the highest number that goes in all these three numbers. So HCF equals 1, and the LCM of these three numbers is simply going to be the product of these three numbers. So LCM is equal to, so we're going to take the highest power of each of the prime factors. So the highest power of 17 is 17, and the highest power of 23 is 23, and the highest power of 29 is 29, and the highest power of 1 is 1. Okay, so the highest power of 17, okay, is 1. Okay, 17 power 1, 23 power 1, 29 power 1, and 1 power 1, right? So 17 into 23 into 29 into 1, so that's going to be 11,339. So we just multiply these and we get the LCM of these three numbers. Okay, in a similar way, you can calculate the LCM and HCF of the third example as well for 8, 9, and 25. Again, we don't need to verify whether the product of HCF and LCM is equal to the product of the numbers, because that applies only if it's two numbers. Okay, since we are calculating the HCF and LCM of three numbers here, the product of the HCF and LCM is not going to be equal to the product of the numbers themselves here. Okay, so that applies only for two numbers, remember that. Okay, this is a fairly straightforward one. You're given the HCF and of these three of the two numbers as 9, and you're asked to find the LCM. Okay, so because it's two numbers, we know that the product of the HCF and LCM is equal to the product of the numbers. So HCF of A and B into LCM of A and B, so when you have only two numbers, is equal to A into B. So that means LCM of A and B is equal to A times B divided by HCF of A and B. So in place of A and B, we have 306 and 657. So LCM of 306, so 306 and 657 equals the product of the two numbers, so 306 into 657 divided by the HCF. So the HCF of these two numbers is given as 9. So this calculation will give us the LCM of these two numbers, and when you calculate this, we get 22,338. Okay, so the LCM of these two numbers is 22,338. So rather than factorizing both the numbers and then finding the LCM, we use the relationship that the product of the HCF and LCM is equal to the product of the two numbers. Okay, so that applies, this relationship applies only when we're dealing with two numbers, a pair of numbers, that is. Okay, let's move on to the next question, and here again it's something similar to what we did in the previous class. We checked in the previous class whether 4 power n ends with the digit 0. Now we are given 6 power n. So how do we go ahead and see whether 6 power n will have an answer ending in 0 for some value of n? Okay, is there any value of n which, when substituted in 6 power n, results in a number that ends in 0? So if the number ends in 0, then the one of the factors of that number should be 5. Let's see if we can represent 6 power n in terms of some prime factor that involves the number 5. So let's begin with 6 power n. So 6 power n. Now we can write the number 6 in terms of its prime factors, which is 2 and 3. So that's 2 into 3 power n. So that's 6 power n. And we can write that as 2 power n into 3 power n, right? So 3 power n. So any 6 power n will result in its prime factorization in terms of 2 power n and 3 power n. So the only prime factors that are involved in 6 power n are 2 and 3. So the answer is always going to be 2 power n into 3 power n. So for example, if n equals 1, it will be 2 power 1 into 3 power 1. If n equals 2, it will be 2 power 2 into 3 power 2. So the only prime factors involved are 2 and 3. And clearly, for 6 power n to end in 0, 5 must be a prime factor. So let's write that. For 6 power n to end in digit 0, 5 must be a prime factor. 5 must be a prime factor. Clearly, 6 power n does not have 5 as a factor. So we say that since 5 is not a prime factor, for 6 power n, not for, of 6 power n, for any value of n. So 6 power n cannot end in digit 0. Okay, so how we are able to show this? Because we are clearly seeing that the factors involved in 6 power n are only the numbers 2 and 3. The prime factors are 2 and 3 only. There is no 5 involved here. So if any 6 power n ends in the digit 0, then 5 must be one of the factors. And since 5 is not a factor for any of the 6 power n's, therefore none of the 6 power n's will result in an answer that ends in the digit 0. Okay, so that is how we go on to prove this particular kind of problem using the prime factorization idea. Okay, moving on to the next question. We are asked to explain why these numbers are composite numbers. So composite numbers, again, for the fundamental theorem of arithmetic states that any composite number can be represented as a product of some prime factors. So let's take each of these. So 7 into 11 into 13, 7 into 11 into 13 plus 13. Okay, so we need to show that this result can be, or this number can be represented as a product of prime factors. So since we have 13 here and here, we can take 13 as a common factor. So when we take 13 as a common factor, we will have 7 into 11 plus 1, because we have taken 13 as a common factor. So we get 13 into 7 into 11 plus 13 into 1 is 13, okay, which is the same expression as on the left hand side here. So it's 13 into 7 into 11 plus 1. So that is basically equal to 13 into 7 into 11 is 77. 77 plus 1 is 78. Now we can represent 78 in terms of its prime factors. So 13 into 78 itself can be written as 13 into 6. And now 6 can be broken down further as 13 into 13 into 3 into 2. Okay, so now what we see is that this number that we were given initially, that can be represented as a product of some prime factors, which is 13 into 13 into 3 into 2. And so therefore, since we are able to represent the left hand side as a product of prime factors, that means the left hand side number, whatever it is, it has to be a composite number, because the fundamental theorem of arithmetic states that any composite number can be represented as a product of its prime factors, right? Or product of the powers of its prime factors. In this case, it is in terms of the powers, we can write 13 square into 3 into 2, and if you calculate, you will see that the left hand side and the right hand side are the same. So we can say that since 7 into 11 into 13 plus 13 can be represented as product of powers of prime factors. It is a composite number. Okay, so that's the way to go about it. So we have shown that the left hand side expression can be represented in terms of the product of prime factors. So therefore the left hand side expression that is given to us is indeed a composite number. Okay, we'll take a similar approach to solve the next question as well. So we have 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5. So again, we can take 5 as a common factor. So we will have 7 into 6 into 5. Since we've taken 5 outside, we don't need to write that. So into 4 into 3 into 2 into 1 and plus 1. Okay, so we'll have the same combination again. So it's 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 into 1 is 5. Okay, we'll have the same expression. So now we get this as 5 into, when you multiply 7 into 6 into 4 into 3 into 2 into 1, what do we get? So we get this as 1008 plus 1. So we get it as 5 into 1008 plus 1 is 1009. And we now need to check if 1009 can be represented as a product of prime factors. And when you check that, you will find that 1009 is in fact a prime number itself. So we can't simplify this any further, or we can't factorize 1009 any further. So we'll just have to leave it at that. So it's 5 into 1009. So now the left hand side expression that was given to us is being represented as a product of prime numbers. So therefore the left hand side must be a composite number. Again, so we'll write the reason, since 7 into 6 into 5 into 4 into 3 into 2 into 1 plus 5 can be represented as a product of prime factors it is a composite number. Okay, all right, so fairly straightforward. Okay, so what we have done is we have basically used some elementary procedures to simplify the calculation, and then gone on to show that the given expression can be represented as a product of prime factors. And since it is possible to represent them as a product of prime factors, it means that that expression is denoting a composite number, because the fundamental theorem of arithmetic states that any composite number can be represented as a product of its prime factors. Okay, moving on to the last question of this exercise. Okay, we are given that there is a circular path around a sports field, and two people, Sonia and Ravi, each of them, Sonia takes 18 minutes to go one round of that field, while Ravi takes 12 minutes to go around the field. Okay, so suppose they both start at the same point and at the same time and go in the same direction. After how many minutes will they meet again at the starting point? So Sonia takes 18 minutes to complete one round, and Ravi takes 12 minutes to complete one round. So suppose the just to illustrate the how it is working here. So it's a circular ground, and let's say they both start at some point, let's say at 12 o'clock. So they both start at the same time and they both move in the same direction, and after 12 minutes Ravi will reach here. Okay, Ravi will complete one round after 12 minutes, and Sonia will complete one round after 18 minutes. So at 12 minutes, Ravi would have reached here at the starting point, but Sonia would not have reached yet, because Sonia requires 18 minutes to reach there. So they cannot meet here. They will not meet after 12 minutes or 18 minutes. So that means they will not meet at the first round. So when they complete the second round, okay, when Ravi completes the second round, he would have spent another 12 minutes, so that will be 24. And when Sonia completes her second round, she would have completed that at the 36th minute, right? It's because each round Sonia takes 18 minutes. But Ravi has already completed 2 rounds in 24 minutes. And when he does the third round, that's another 12 minutes. So that will be, okay, this is 18 here, okay? So 18 plus 18 for the second round. So by the time Ravi completes 3 rounds, Sonia has completed only 2 rounds. And we see that 12 plus 12 plus 12 is 36. And 18 plus 18 is also 36. So that means after 36 minutes, they will both meet at the starting point. However, Ravi would have completed 3 rounds at that point, and Sonia would have completed only 2 rounds. Now, how to approach this problem is, basically, this question is asking us to calculate the LCM of 18 and 12. So now all we have to do is compute the LCM of 12 and 18, and that is basically the result that we are going to get, which is 36. Okay, so again, to find the LCM, we write them in terms of their prime factors. So 12 is 2 into 2 into 3, which is 2 power 2 into 3, and 18 is 2 into 3 into 3, right? So that will be 2 into 3 power 2. So to find the LCM, we take the greatest power of each of the prime factors and multiply them. So the greatest power of the prime factor 2 involved in these prime factorizations is 2 power 2, and the greatest power of 3 is 3 power 2. So the LCM is simply going to be LCM equals 2 power 2 into 3 power 2, and so that's 2 power 2 is 4, and 3 power 2 is 9. 4 9s 36. So the LCM is 36, and that is what we figured out here as well. Okay, so this is an indirect way of asking to calculate the LCM of 2 numbers, so LCM of 12 and 18. Okay, so you need to be able to understand what is being asked in such kind of word problems. It could be fairly straightforward. All you have to do is compute the LCM of 12 and 18. Okay, so we'll stop here for now, and we will continue with the next part of chapter 1, which deals with irrational numbers and how to prove whether a number is irrational or not. Okay, we'll cover that topic, that discussion, in the next video, and then we will move on to solving some exercise problems related to the idea of irrational numbers as well. So we'll see how to prove that a certain number is irrational. Okay, we'll stop now and we'll continue in the next video.